thank you everybody for joining what is the first of hopefully a number of events that SEED hopes to run with the Scottish Hydrogen and Fuel Cell Association, led by Nigel Holmes, who I've known for many years, since my time at Heriot-Watt University. In some senses, it's an unusual collaboration, but what we hope to achieve is through SEED members joining the Fuel Cell Association members, an opportunity to turn aspiration and hope as it relates to the development of a hydrogen fueled economy into real tangible outputs, something which the SEED membership excel at. Jane is going to control slides, so if I ask Jane to move over to the next slide, we'll go through some simple housekeeping rules. Jane, next slide. Thank you very much. So usual housekeeping on this, if you can all turn off your audio so we don't get noises off. We'll be recording the session and make it available. It usually takes a couple of days at least before that's available. We'll do that along with the list of delegates attending today, plus the presentations. You can turn your cameras and speakers back on should you want to contribute to the question and answer session at the end of the event. We hope you'll use the chat box to pose questions, to introduce yourself to each other. Be particularly somebody out here with a cup of tea or coffee in the background. If you could mute your speaker, that would be your microphone, that would be good. Please do use the chat function for questions and points you'd like to raise, particularly if you're looking for collaborations and you can see ways where the SEED or SHEFCA membership can help you. Jane, next one, please. Jane. Thank you very much. So the running order, after a few minutes from me, I'll introduce you to Nigel, who is going to be our moderator for today. I'll let Nigel subsequently introduce the speakers as we go through them. I want to tell you a little bit about SEED. We're fundamentally a Jane, can you? Jane, next slide, please. And just a reminder again, please, people turn their microphones off. SEED's fundamentally a membership organisation, and through SEED's membership, businesses have the opportunity to raise operational issues and reach out to other members for a solution. How we work with our members depends really on the nature of the problem that we are posed with. Most commonly, the challenges that a member may have is of a similar nature to something which another member will already have encountered, and we'll put together a workshop drawn together from individuals from companies who've already expertise in that area to share potential solutions for mutual benefit. However, you may well have a completely unique problem, in which case SEED's also the place to come to. It's where it may be possible to engage in a one-to-one project with another member company or one of our academic partners. We also regularly offer events like today's to both members and non-members to address the opportunities that may exist to engage in the contemporary challenges that face Scotland and beyond. Membership benefits include the new pilot programme that SEED's launching with our member companies called the Mentoring Mix-Up. This has been run in conjunction with Skills Development Scotland, and the programme will support engineering and manufacturing companies retain and help employees develop through learning from senior leaders across the industry. But places are limited on this, so if you're interested in the membership mix-up, please do get in touch now. We also offer a Growth 500 executive leadership programme aimed at SMEs seeking to grow their business, and an executive leadership program called Leading from the Front, which is a practical and focused program for members to share best practice with their contemporaries and peers. In fact, it's only yesterday that a Scottish Government approached SEED and pointed out that it's this peer-to-peer membering that can be facilitated through SEED's members and organisations that is the most valuable asset for them when they're looking for ideas and support to develop new opportunities. So, Jane, next slide, please. So I'm Patrick McCarthy. I'm the program manager of something called the Advancing Manufacturing Cluster Building. This is an initiative that's open to and available to SMEs across Scotland, where the resources, facilities, support and expertise is available to micro SMEs and SMEs at no cost. It consists of 12 projects, one of which I think the aerospace visualization project is Danny, I think he's on this particular call. But there are 11 others spread across the rest of the country. If you want to know more about the, and you can see where those projects are and what they focus on from the slide. If you want to know more, please do give me a ring. I think that's about all I want to say about SEED. So I'm going to hand over now to Nigel to let you have the main event. Thanks, Nigel.
Patrick, thank you very much for that introduction. Good morning and welcome to this webinar on hydrogen aviation opportunities. I'm Nigel Holmes. I head up the Scottish Hydrogen and Fuel Cell Association. Next slide, please, Jane. And we have about 150 members. I'm delighted to see the turnout today. I'm looking down the attendee list and thinking this would be great to be in the same room and actually see all of you in person, but it's not the case. But we've got people from industry, we've got people from academia, we've got development agencies, a great spread of people, and that's important because we need to find the ways of actually making this opportunity turn into real progress. Next slide, please. And the challenge with hydrogen aviation is very much about trying to replace a very well established sort of technology, engines running on fossil fuels, with a zero emissions alternative. But the great thing is that Scotland set some ambitious targets around decarbonising aviation, Highlands and Islands to be the world's first net zero aviation region by 2040. So that kind of sets the ambition, and there's already projects happening. A couple of pictures here. One's of the High Flyer 1, the 6-seater Piper. The other picture is Project Fresson with the twin-engined Britain Islander. Next slide, please. And also going forward, it's not just about the aircraft themselves. It's about the environment the aircraft are working in, and that comes back to the airports. So, for example, in Orkney, a lot of work is going on with the Sustainable Aviation Test Environment, also known as the Aviation Test Hub in Kirkwall Airport. So, just to show that that this is actually going to be relevant sooner rather than later. On the tarmac is a Britain Islander, which is a nine-seater aircraft. They use them regularly in Orkney, and it would be great in a few years' time to be able to go up to Orkney and actually fly between the islands on one of the first hydrogen aircraft. So fingers crossed that'll be happening sooner rather than later. Next slide, please. So going now into the content of today's event. It's very much about starting to hear from our speakers. We've got a great lineup this morning. Oh, there's one more slide. I forgot about that one. As well as Orkney, what we're seeing are locations like Cromarty, where this is potentially about aviation, but they could take it a bit further. They're looking at the opportunity for space, sort of hydrogen and satellite launches from areas like Cromarty. Again, it's not just about Cromarty. There's other locations in Scotland also available. Jane, next slide, please. So going forward, as I said, now we want to have the speakers today, starting with Cedric Road of Ricardo. So Cedric's been with Ricardo for over 10 years now, working on hydrogen fuel cell developments. He's their global expert for fuel cells. And previously to be with Ricardo, Cedric was working in the automotive sector. So, Cedric, I'd like now to pass over to yourself. Just take us through some of the development of fuel cell systems, light aircraft, and where we've got to now, and maybe some insights in terms of what happens next. Cedric, over to you.
Thank you very much, Nigel, for your kind introduction. Good morning, everyone. So I will start with a quick introduction of Ricardo, my company, which is based in the UK, but we are worldwide, as you can see on this map. So we are a global environmental and engineering consultancy that has been funded by Sir Harry Ricardo over 100 years ago. Historically, we have started with automotive engineering activities, especially on the internal combustion engine with Sir Harry Ricardo activities. But we have diversified a lot, especially in the last 20 years. And we are now roughly 3,000 people across 51 sites in different 20 countries. I will now talk about our activities in the aerospace domain, because we talked today about the fuel cell for light aircraft. Next slide, please. So within our automotive industrial division, where I'm sitting, we have expertise and capabilities across engines, transmissions, batteries, fuel cells, electric machines, power electronics, low carbon fuels and thermal systems. So the whole system engineering activities that integrate also all those systems together for implementing onto a vehicle. So we deliver projects for customers ranging from policy studies and thought leadership through to complete turnkey production programs. And I will show you an example of what we are doing on the next slide with our the project Fresson that has been announced earlier this year. It's a project led by Cranfield Aerospace. So we are a member of the project as it is shown here, such as Innovatus, Britain Norman. The project is funded by ATI. And you can see a link to the webinar that we have done between Cranfield Aerospace Solutions and Ricardo back a month ago, actually, presenting in more detail the project Fresson from the perspective of Cranfield Aerospace Solutions and Ricardo supporting the development of the fuel cell system integration. The next slide, I will explain a bit what the fuel cell is, if people are not everyone is familiar with. So it's a way to produce electricity using hydrogen and ambient air. So in the Fresson project, we work with the proton exchange membrane, what we call PEM fuel cell. So the PEM fuel cell is the most common fuel cell technology used on several applications, from forklift truck to buses, trucks, trains, marine vessels, and now also aerospace. So the fuel cell system works with hydrogen from storage device, that could be a compressed gas tank or in liquid form, and oxygen from the ambient air, and they convert the chemical energy of the hydrogen fuel directly into electricity via a membrane sandwiched between two electrodes. The fuel cell system is using fuel cell stacks and ancillary system, also called balance of plant, BOP. You will hear this acronym later. The BOP is developed to provide the hydrogen and the air at the right temperature, pressure, mass flow rate for the fluids, and relative humidity on the anode, where we feed with hydrogen, and the cathode, where we feed with the air side. So the hydrogen molecules donates its electron at the anode, leaving positively charged protons. So the electrons travel through the circuit and protons through the membrane to the cathode, where they form water. Water is the only byproduct, so it's a zero emission, zero carbon and zero pollutant emission source powertrain for the aircraft. The heat is removed through a cooling system, which is not shown on this schematic, that is from Intelligent Energy, who is a fuel cell supplier based in the UK. Next slide, please. On the next slide, I'm presenting here also an extract of a report, which is a source. The source is mentioned at the bottom in the footnote. which is the hydrogen powered aviation, and it highlights for different types of aircraft what would be the powertrain in the next 10 to 15 years when we use hydrogen with the different size of planes. We work on the Fresson project on a commuter less than 19 people, 19-seater, with less than 500 kilometer range and a cruise speed below 300 kilometers per hour, using compressed gas tanks and electric motors, of course, for the thrust. There's no auxiliary power unit. The other, I will not describe all of them, of course, but that highlights the context of the hydrogen used on aircraft, different depending on the size. If it is directly into fuel cells for commuter and regional aircraft, or into hybrid powertrain using potentially a fuel cell as an auxiliary power unit. And for larger aircraft, medium to long range, we see the future would be using hydrogen gas turbines, and the fuel cell will be also an auxiliary power unit, part of the powertrain system, or just for providing electricity on the ground. So that sets the scenes for the overall context for the next 10 to 15 years. Now I will continue into the development about on the next slide, please, about the fuel cell system for the Fresson project as an example. So this is extracted from the webinar that was presented a month ago, roughly. We have here a comparison between the fuel cell systems that you can find nowadays as fleet demonstrations for commercial vehicle trucks, like Hyundai trucks or Toyota portal projects in the US. Hyundai it's in Switzerland, or passenger car like Hyundai Nexo, Toyota Mirai. What is the benchmark in terms of size performance of the fuel cell system? So the automotive 2020 is what we can find now on the street. Of course, there's not a lot of vehicles using hydrogen fuel cells, but it is growing. And those fuel cell systems are not suited like for aerospace applications because they are quite heavy systems. The efficiency is quite good, but the fact that we have such a heavy and bulky system that is on passenger car and commercial vehicle trucks is not really suited for aerospace applications. So this is why we need to bring bespoke solutions for the fuel cell stack and the balance of plant, all the ancillaries around the fuel cell stack to control the hydrogen and air and the cooling circuit. So you see that for the aerospace target for 2024, which is targeted for the Fresson project, we try to be, we say, in terms of packaging, a bit better than the automotive domain, but in terms of gravimetric specific power in kilowatt per kilogram, it's much greater than what we can find or what we will find in 2024 automotive domain at 1.5, at least 1.5 kilowatt per kilogram versus the 0.9 kilowatt per kilogram passenger car domain. So this is really because the weight, of course, is to be avoided on aircraft, and that gives us, Ricardo, a lot of activities into the development of the fuel cell system. On the next slide, please. We will see the challenges that we have for developing the fuel cell system for the aircraft. So we have some sketches here around the nacelle and how to integrate the fuel cell system into the nacelle of a Britten-Norman aircraft. That is a packaging, of course, challenge. There, as I mentioned, we have also the challenge of the weight or specific power gravimetric. We need also to be able to test large power of fuel cell systems. We talk about more than 250 or 300 kilowatts per wings for light aircraft. There are discussions about megawatt or 2 megawatt fuel cell system installation for larger aircraft. So Ricardo is developing also installation in that sense. And the performance also needs to be tested at different ambient temperature and also altitude. And before testing, we need to simulate. So we develop tools, techniques, software to do that. We have also partnership with the fuel cell stack suppliers that we are going through because not all the fuel cell stack are available for aerospace applications. And finally, the transient response is very important because we would like to have transient response as quick as the conventional engines or gas turbines that are used on aircraft, but the fuel cell is a bit slower. So that means that we need really to improve the time response of the fuel cell stack and its system. On the next slide, I present, now it could be a bit busy slide. I will not detail all the boxes, but it's to explain that at the center of this slide, we see the stack, which is what I presented before, producing electricity from hydrogen and ambient air. And it requires different ancillaries, components on the hydrogen loop, the air loop, boosted air, and the cooling circuit loop in order to control pressure, temperature, mass flow rate, relative humidity, and stoichiometry at the inlet of the stack. And for that is only showing the complexity for one stack. But for large applications where we need several hundreds of kilowatts of electrical power, we will have to have multiple stacks because we cannot oversize the stack to 300 kilowatt, 500 kilowatt. We need to bring stacks of 100 to 150 kilowatts. That is the typical size of a stack, and bring them together and then plug the hydrogen, the air, and the cooling circuit in the most efficient way, because there are electric ancillaries that consume electricity, and the lightest way and in the smallest package. So that is the challenge that the aerospace is asking us to solve. And of course, once it's done on aerospace, hopefully it can come down to terrestrial applications. And we think about, for example, motorsport applications. So we will have multiple stacks, and you can imagine those loops will get more complex, but we don't want to have a reproduction from one stack to another and copy-paste the components for each stack. So we want to group the requirement and the components for the air loop, the hydrogen loop, together in order to have potentially only one or two components to bring hydrogen or to bring boosted air to the stack, and not multiple ones once we have multiple stack. I'm conscious it's a bit complex slide, but if you have any question, please let me know and we can follow up later. Next slide, please. The next slide is presenting the process to develop the multiple fuel cell stack balance of plant. So all the ancillaries I mentioned, the complexity of having multiple components, valves, pumps, blower, compressor, charge air cooler, humidifier, all this relies into the complexity of the development of the fuel cell system. The stack itself is complex. It is, let's say, a kind of shoebox or large shoebox that will produce electricity if you bring the right amount of hydrogen and air together. And that's what the balance of plant does. So to do that, we set the target on the left-hand side. That's the first part of the system engineering activity that we develop. And we use different tools that we have developed in Ricardo called 0D tool. The first one is architecture independent modeling to size the fuel cell stack versus the battery, because there's always a buffer on the different applications. We try to minimize the battery on some applications and try to not to use one. And this is why the transient response is important, to avoid needing a large buffer. We have also tools to develop the balance of plant, what we call Ricardo Fuel Cell Architect. And all this helps with the definition of all the functions what we need to do in terms of cooling, heating, humidifying or dehumidifying, controlling the pressure. That helps to list all the components that we will have at the end as a design and to be developed further into test activity. So the 0D tool will help to have also energy balance, to understand also how to improve further the efficiency overall of the fuel cell system, which should be as close as possible to 50%. Finally, when we move into further on the right-hand side with the fuel cell balance of plant optimization, we use 1D tools. So that means that we use thermohydraulic, electrical, and chemical models in order to refine the specification of all the components of the fuel cell system, and also be able to do transient analysis. So the transient performance will be assessed at this stage. Once we have a transient model, we go into reduced order model techniques that we have developed in the last 20 years for different applications. And that means that we can have models that are very quick to run, quicker than real time, and can be implemented into control units that could interact with the flight controller in the future on the aircraft. And we can use advanced control techniques, such as model predictive control, in order to optimize the energy consumption on the aircraft of all those ancillaries, compressor, blower, pumps. Finally, what we can have also is an electric horizon. That means that we will plan will happen next, because we'll have a link with the flight controller, with the satellite navigation, positioning of the aircraft into the space, into the sky. And that means that we can know what will happen next. And by doing so, we can control better and minimize the energy consumption of the different ancillaries. Now, having said that, so I can show where we are. I'm sorry if you hear some background noise. I've got some work at home. Next slide, please. So the status of the different challenges I've mentioned previously at this stage on the Fresson project, what we have presented on the webinar last month, is we have ticked the box of all those challenges at the moment at we say digital level, paper level, desktop level. And the next stage will be to go into the test activity in the coming month. So we have now packageable fuel cell systems on each wing with the right performance and weight. We have also in Ricardo invested into 400 kilowatt fuel cell test chambers in Shoreham by Sea, South London. That will be available Q1 2022. We have also the capability to test hydrogen engines, combustion systems. We have also developed a development validation plan, and we have demonstrated by simulation that we can operate at different ambient conditions and altitude levels. We are also in the process of selecting the different suppliers for the fuel cell stack and also the different components of the Banzer plant. And the model has been used to assess the transient response of the fuel cell system. On that note, I will hand over back to my colleagues, and I will be happy to take any question you have at the end, I think.
Thank you, Cedric. And we have a little glimpse there of the a spider chart, which just shows the different status of the technologies as we start to develop them. And one of the things you mentioned was about weight being important, which brings us a nice segue into our next speaker, Ruan Swart, Chief Executive of the Innovators Technologies, who are looking to develop a lightweight hydrogen storage tank, which is going to be critical. You know, if we're going to actually get these planes off the ground, we're going to have to work out how to capture the hydrogen and keep it in the right place. So, Ruan, over to you.
Thank you very much, Nigel. Good morning, everyone. And thanks also to Patrick for including us in today's webinar, and also for all of you listening today. I'm here to present our Scottish hydrogen fuel tank, which we believe is the next generation of high pressure storage tanks, as an opportunity to decarbonise aviation, as well as multiple market sectors. Throughout this presentation, I'm going to concentrate on three main words, which is weight, gravimetric density, and form factor. These are the key features of a tank that either enables or constrains a hydrogen fuel cell project. And our Scottish manufacturing next generation tanks sets a brand new benchmark on each of these three key performance indicators. So next slide, please. Thank you. The shift in storage technology, it utilises the latest patented and protected aerospace technology and composite manufacturing process and methods that produces lightweight pressure vessels within the aviation sector, as we're part of Project Fresson, and also other market sectors that we are currently looking to engage with. This ensures a tailored product that fits any form factor and application and provides the best market gravimetric density available. Our product is 25% lighter. It's compared to current industry solutions, as you'll see in a few slides' time, which ultimately results in a 30% increase in gravimetric density and a 5+ increase in more hydrogen per unit. So this is obviously size and application dependent. Thus leads to a greater range in certain applications and also payload capability for the multiple fuel cell market sectors. Within our product as well, we have the ability to embed sensory systems within the composite structure to enable active health monitoring, during servicing, and with a future view of during the actual operation of the tank on whatever application it's suited towards. So all of this means that we are fundamentally different. We are lighter and more compatible without compromise within any application or market sector. Next slide, please. On your screen, you can see the industries and applications that we serve or intend to serve. We intend to satisfy these market sectors by manufacturing our products in Scotland within the ecosystem of the Scottish hydrogen supply chain, by facilitating environmental change throughout the hydrogen power value supply chain, where we can deliver the greater performance in terms of system mass, payload capacity, and range. So more hydrogen equals a further distance traveled or more operational benefits in certain applications. The Shift product line is also designed to be very scalable and modular in order to meet the key performance requirements for each application or customer. Next slide, please. Here's a technical comparison on your screens, showcasing and comparing our Shift products against the leading market solutions which are currently available. The comparison highlights the vessel storage density, the hydrogen storage mass, and the total unit weight, which are the main comparable parameters that you would see across the hydrogen storage sector. Our product achieves equal or greater gravimetric density for a variable amount of hydrogen storage capacity, and this is also size and application dependent. Even with the more competitive tank solutions on the market, Shift still delivers an optimum solution, and we deliver a delta that makes a difference in hydrogen fuel cell projects by enhancing applications performance, lowering the weight, and optimally can be integrated within the form factor of the application. Next slide, please. So as my colleague Cedric mentioned, Project Fresson, we are currently on that project and working alongside them. And as an example which emphasizes the previous claims in the previous slide, is I'd like to express that the practical impact of our design and our product is currently happening as we speak. The Project Fresson, without repeating what Cedric said, has been funded by ATI, Bayes and Innovate, and we're currently working with Cranfield Aerospace, with Ricardo and the OEM Britten-Norman to electrify the BN Islander aircraft against its avgas predecessors to become the world's first truly green passenger carrying aircraft. And Project Fresson, from our point of view, really expresses why our Shift tank is one of the main innovations in any hydrogen fuel cell system applications. And just on our final slide, thank you very much, Jane. Just to state, we are an innovative Scottish SME with a multidisciplinary engineering team across various industry sectors, and we call upon deepest engineering resources and disciplines. So for any further information, please get in contact with myself at the email address you see there, as well as any questions at the end of the webinar. Thank you very much for your time, and I will hand over to Nigel. Thank you.
Ruan, thank you very much for that introduction to the work you're doing. Weight, clearly important. Get the weight down, get the planes off the ground, and it's not just the planes. We focus so far on the aviation opportunities with conventional planes, but going forward, the options could also involve drone deliveries, drones for a whole load of activities that currently would be quite expensive or difficult to do. And this is one of the areas that Stephen Cunniff of Doosan Babcock is going to pick up in his presentation. So Stephen, over to yourself.
Thanks, Nigel. And thanks to Patrick as well for the introduction, and thank you to everybody joining today. So today I'm going to talk about the role of hydrogen and what that role that plays in sustainable aviation, and how the developments in ground-based transport, airport operations and UAVs can help pave the way towards sustainable aviation with hydrogen. At Doosan Babcock, hydrogen represents an exciting opportunity across many of our sectors. Give this opportunity to look at various technology solutions for our industrial clients. The services we typically provide range from concept studies through to full EPC contracts, and integrating hydrogen solutions is becoming more central to the work we carry out on a day-to-day basis, and we're currently involved in a number of hydrogen supply and technology integration projects. Our experience in process safety and high integrity applications give us an interest in the emerging requirements around hydrogen and sustainable fuel development. The challenge in the aviation sector is clear. Emitting 0.9 gigatons of CO2 per year and accounting for 2 to 3% of the global carbon emissions worldwide, it's a big challenge. Pre-COVID, it's also a sector that was experiencing significant growth and is projected to continue growing shortly. The industry is now actively seeking alternatives beyond jet fuel and beyond efficiency and logistic improvements at airports and with aerospace OEMs. Biofuels and synfuels hold advantages in terms of development pathways, in that they can utilize existing airport infrastructure and refueling systems. Biofuels offer significant fuel life cycle CO2 emissions, but obviously are reliant on the availability of feedstocks, and those feedstocks can't compete with the food chain. Synfuels offer the range for long-haul civil aviation, which currently hydrogen would need to look at liquid hydrogen systems to compete with. But synfuel has the potential to work with hydrogen and CO2 to create a jet fuel alternative. However, hydrogen is the only alternative to jet fuel that can cut all the CO2 emissions from the propulsion, and additionally it can be used to decarbonize the airport itself. So speaking a bit about hydrogen and the airport energy ecosystem, the hydrogen can play multiple roles in the airport energy ecosystem, from heating, cooling and powering the airport buildings themselves, to decarbonizing ground transport. It offers a single fuel that can deliver solutions beyond all this, and it also paves the way towards flight. The picture around hydrogen's place in international airports is still emerging, as complex fuel handling strategies will need to be considered, with multiple fuel pathways needing to be considered at airports. However, the drivers towards the hydrogen pathway can be determined by both top-down drivers and ground-up enablers. Major Tier 1 aerospace OEMs are looking at how they position their strategies that will now allow the supply chain to follow. However, from a ground-up approach, there are major regional incentives for hydrogen production and demand cases, which pave the way for hydrogen infrastructure to be introduced to the airport and help de-risk the pathway to hydrogen flight. And a case study on this was our involvement with EMEC in the Kirkwall Airport hydrogen CHP, where Doosan Babcock worked with EMIC to introduce the first 100% green hydrogen combined heat and power system in the UK at Kirkwall Airport. The project's looking at providing heat and power to the airport buildings, and Doosan worked with partners 2G to introduce the CHP to the site. The reason this is such an interesting development comes down to the coexistence with other projects looking at hydrogen in flight in the SATE initiative that's happening in Orkney, and their connections into the High Flyer project previously referenced. Another application that helps to move on hydrogen in light transport and UAS applications is the drone. So drones are a great technology for fuel cell and hydrogen, and provide an important role in enabling that pathway in hydrogen innovation. The Doosan mobility innovation drones were launched in 2019 and have been used in a number of applications showcasing the advantages of hydrogen in flight duration and the delivery distance over conventional battery-powered drones. So featured in terms of the Doosan drone compared to a comparably sized battery drone, the delivery distance, that's one way is 40 kilometers, so return it can do 80 kilometers on a single tank. So it gives a great ability to cover area for various survey or inspection works, and of course we're looking at the option for delivery as well. The hydrogen fuel cell, as Cedric has gone into in some detail, offers greater energy density over batteries, and together with the modular integrated Type 4 hydrogen tank that Doosan has also developed, offers a solution that allows users the ability to switch out the hydrogen bottles really quickly. The tanks have been designed to be tip-ed compliant to allow them to be transported to sites or to the point of use. It's an air-cooled fuel cell, and it's a modular solution that can be expanded to suit the requirement. As I've shown in the previous slide, the current drone offerings are multi-copter and virtual takeoff and landing fixed wing. However, there's other opportunities to expand beyond this with larger fuel cells and fuel cell types coming. So with regards to how this has been used, I'll briefly touch on a case study we've done with DMI in Korea, where delivering to 3 islands off the coast of Jeju Island. The DMI drone did 4 round trips covering 9 kilometers to deliver PPE to users due to ferry constraints. It was enabled. The most important thing about this particular case study, it was beyond visual line of sight. So there was a waiver from local government to allow this to take place. And it was a success, even when the LTE connection was momentarily lost. The DMI control system allowed the drone to continue its automatic mission flight. And just to touch on some of the interfaces here, you get a live readout of the health of the fuel cell system, as well as a visual representation of your mission. And just to give reference to the refueling, while not on this mission, Doosan has developed with UK-based NanoSun a mobile cascade refueling system. So Nansen have developed this specifically for DMI applications, which allows the drone to refuel those cylinders at site in less than 5 minutes. So it's a low cost option. And speaking more broadly at wider developments in the UK, the industrial cluster decarbonisation initiatives sees major blue and green hydrogen projects being announced. With many of these close to major ports, it represents a major opportunity to develop offshore beyond visual line of sight test beds, specifically for hydrogen drones and hydrogen cargo drones. This is particular relevance to the offshore wind market, where these ports could be used to service the rapid expansion of the offshore wind industry, of which the UK is a leading force. Additionally, there are a number of offshore and nearshore wind to hydrogen projects which are either in development or being considered. These could pave the way for offshore refueling and the potential for these drones and cargo drones to offer inspection and service or provide spares or lifeguard assistance for offshore wind and gas assets. And just to touch on the Scotland piece within this, Scotland's providing a major role in providing sustainable aviation test beds, which there's two referenced on screen. So the SATE Sustainable Aviation Test Environment is operating out of Orkney with the likes of the High Flyer programme already associated with it. And additionally, up in Montrose, we've got the Mercury drone port, which importantly is looking at building out that beyond visual line of sight drone corridors for vessels that are anchoring offshore wind farms, or up to regional oil and gas platforms. So in conclusion, hydrogen fuel cell drones are well placed to service some of these offshore opportunities, while also helping to de-risk some of the infrastructure around airports for introduction of hydrogen in sustainable aviation. Additionally, the role of hydrogen in decarbonising airport operations themselves cannot be underestimated, and Doosan are very interested in helping to develop both opportunities. Thanks very much.
Stephen, thank you very much. And yeah, that was a really good introduction to some of the work that's starting to develop in the use of drones. But Stephen, you also mentioned the importance of airport operations, and our next speaker, Ed McFarlane of Abbott Risk Consulting, will hopefully touch on the importance of airport operations, but within a whole system safety context. And this covers activities in particular with refueling, where you could be handling significant quantities of hydrogen, whether that's gaseous hydrogen or liquid hydrogen. So Ed, over to yourself.
Thanks, Nigel, and morning, everyone. Thanks for coming along. Hopefully you'll find this useful, and this will prompt some ideas for Seed members to follow up on for market opportunities and potential avenues for collaboration. Good, next slide, please, Jane. So just put this in context, Abbott Risk Consulting is a safety engineering consultancy, and so my presentation is very much from a safety perspective, but hopefully this highlights another one of the other sort of complex systems and implementation challenges. I'm just going to quickly run through sort of putting refueling in context, a very quick summary of hydrogen characteristics and how that then interacts with refueling, current hydrogen application in the aviation sector, current and future, and then the implications for refueling activities, current and future. Okay, Jane, can you go to the next slide, please? So currently, the aviation sector is primarily a kind of a mono-fuel sector. It's Jet A1. It's broadly a kerosene product, normally fairly high purity, with a number of additives to deal with low temperature and that kind of thing. But essentially, that is the fuel that is used across not just the UK, but the world. In the UK, obviously, most operations are covered by the CAA. I've included a number of links there to various CAA publications, both current and some of them superseded. So CAP 748, which is the main one on aircraft with fueling and fuel installation management. But just to give the members some information to look at. But please be aware that 748 has actually been withdrawn. It is provided there for you as a useful, and it gives you a high level overview of kind of interesting information and useful information. But broadly speaking, for airport operations, it'll be the same broad set of legislation, standards and guidance that are appropriate for any other hydrogen application. So if you're looking at high pressure gas, flammable and explosive atmospheres, and depending on the volumes and specifics of the materials you're using, COSH and COMA. Most of the presentations so far have very much focused on the aircraft. But refueling is about more than just the aircraft or even just the whole airfield. We need to take this proper whole systems approach, which if anyone's heard me speak at other events, know that I go on about an awful lot. What do I mean by whole systems? So Jane, if you go to the next slide. So this picture is of Buncefield. I'm sure we're all very much aware of Buncefield. It was a very significant incident a number of years ago. But why am I talking about this in an aviation context? So tank 12, which is the tank in the upper left corner, was a tank of jet aviation fuel that supplied Gatwick and Heathrow. So aviation infrastructure is far broader than just the aircraft. It is the whole infrastructure and systems that enable and facilitate those aircraft. And we need to be very much aware of this. And Buncefield is a good example. I'll come to it at the end of why I think we need to bear Buncefield in mind when we're talking about the development of this hydrogen aviation sector. So go to the next slide, please. So I'm sure a number of you will be familiar with hydrogen, but just to sort of summarize very, very quickly some of the characteristics of hydrogen. So it's low density, so most practical systems are 350 bar or 750 bar or in that range, so very, very much high pressure systems. Low viscosity, it leaks easily, you can diffuse through volumes of materials, and it can in brittle materials are used, but also it's very buoyant. We all know the Hindenburg and we know about hydrogen, and that's why it's used, but it is incredibly buoyant. It's a very wide flammability range, and it requires very little energy to actually ignite it if you are released. It has a few interesting characteristics. When it actually combusts, it burns in the UV range. So actually the flames are almost invisible in daylight, but an advantage is it doesn't radiate much heat. Although if the flame impinges on something, it is likely to escalate. It has a rapid burning rate. So we have this phenomena with hydrogen called deflagration to detonation transition, DDT, which means that essentially you move from a flashover to what's a proper explosion with a shock wave. This is mostly all the gaseous characteristics, but obviously some other forms of hydrogen or other energy vectors involving hydrogen have been mentioned so far. Principally liquid hydrogen, so this introduces a whole load of cryogenic hazards, including the potential to produce LOX, so to condense water and oxygen out of the atmosphere if you have a release. There are also these other energy vectors called liquid organic hydrogen carriers, such as toluene. These are still very much developmental and have not been deployed extensively. Synthetic fuels have been mentioned, but the one thing that has been mentioned is another energy vector for hydrogen is ammonia, and the marine sector is looking at this quite extensively, but ammonia is toxic. So that's a very quick summary of some of the characteristics. Can we move on to the next slide, please, Jane? So the kind of application of hydrogen and how it is used in the aviation sector has implications for some of the considerations. I've taken most of these from this hydrogen-powered aviation report, which was produced by the FCHJU. Very useful and good high-level summary. Hopefully most members can go and have a look at it and have a read of it. And broadly, the kind of areas that hydrogen has been used as a part of electrical power provision on aircraft. So that's really H2 storage and fuel cell for electrical power. And most of the standards for aviation that are available currently are for electrical power provision, not for powertrain or drivetrain provision. And broadly speaking, our drivetrains are going to split into two, which one is an electrical drivetrain, so hydrogen storage, fuel cell, normally a battery or a capacitor, as Cedric said, and an electric motor, but also the control motors for both the propeller, but also potentially control surfaces and that kind of thing as well, although most of them are still hydraulic. or part of a combustion drivetrain. So again, hydrogen storage or synthetic fuel, combustion engine, piston or turbine, a drivetrain, and then normally an electrical power takeoff. So broadly, those are the 3 areas of application. Next slide, please, Jane. So current application, there has been some hydrogen application in the aviation sector. So broadly, hydrogen generation storage has all been gaseous to date. It can normally either produced off-site and brought in by tankers or in cylinders or what are called manifold cylinder packs, MCPs, or it has been generated, compressed and stored on site. But in that case, you do need an electrical and water supply to site as well, not just the hydrogen. The refueling has been done either directly from the MCPs or the tanks brought to site, or filling of an airside tanker truck, as in the high flyer system with the EMEC truck, driven to the aircraft location and refueled. Or as Stephen mentioned, there is this concept of these cartridge plug-in systems where you have a tank that you can disconnect or reconnect. And broadly speaking, at most airports, therefore, we've got Jet A1 still in use at the site, and we've got hydrogen, but then we also have potentially, because of the battery systems and potential electric aircraft, we've got battery charging with high-powered chargers at the site. Next slide, please, Jane. So what will the future potentially look like? Well, we've got everything we had before, but with hydrogen generation, we will have pipeline delivering. So this is getting closer to the Buncefield system, where we have large volume, large scale generation off-site, and it's then piped to get the throughput required to sites. Refueling will happen the same ways, but then we may have a move of moving hydrogen through pipelines and hydrants at airfield. If you're not aware of this, this is the approach used for most large airports, where you have a system of storage, pipelines to the actual airside or the air apron, and hydrants where the truck comes along, and essentially it's just a mobile pump. It takes from the hydrant to then so the fuel from the hydrant into the aircraft. And we may have similar systems in the future, and this is certainly what's been considered for sort of cryogenic or liquefied hydrogen. But the context is going to be quite complex. We may well have Jet A1 or a synthetic fuel equivalent still being used at site, battery charging for electrical systems, and hydrogen present at the site, but in multiple forms or multiple vectors. So we may well have gaseous, liquefied, potentially LOCs, ammonia, or even some of these solid metal matrix type storage means. And we'll also have parallel use of hydrogen for both electric and combustion drivetrains. Next slide, please, Jane. So in terms of the implications for refueling, so for current application where we're really using tanker trucks to take it to the aircraft, actually the current refueling practice at airports is actually quite well suited to hydrogen. It fits in quite well with good hydrogen practice. So separation distances, earthing of the aircraft, exclusion of ignition sources, and also meteorological constraints and operations. It fits quite well. The high buoyancy of hydrogen means that actually you have no fuel spill, which is an advantage over Jet A1 currently, for gaseous hydrogen anyway. And you can also then, during incidents, you can vent safely, although this assumes no ignition sources overhead. Now, obviously, for an airport environment, that's not necessarily a true assumption. As a high pressure gas, so leak releases can result in debris and or concerns like pipe whip if there's some sort of pipe break, and releases can produce high decibel noise, which obviously is a concern for personnel near them. And it also drives some considerations for maintenance. We need to consider activities that may require hot work or ignition sources, and also when maintenance activities need to be carried out inside in an environment that's dry and free from sort of environmental issues. That may not be possible with hydrogen. It means to vent or depressurize your system to actually get the aircraft inside. There is also a whole lot of considerations for first responders. So there is a whole lot of information. So there's the High Response website, which has a whole host of useful information for first responders. But for first responders, hydrogen has some specific considerations. So as I mentioned previously, the invisible flames, you are encouraged not to extinguish fires. If you do identify them, it's better to let the inventory burn. You need to cool the adjacent equipment in case the flames are impinging on them. And really the approach is to isolate inventories and vent and allow the hydrogen to disperse safely. And Jane, next slide, please. So future concerns in terms of implications for refueling. Aviation refueling will probably be part of an integrated part of a wider hydrogen ecosystem. We saw the image from the Cromarty Firth concept where you have this hydrogen hub concept. We've got aviation, both manned and unmanned, process industry, rail, marine, road, energy storage, and domestic use for hydrogen. There's also these concepts for sort of remote hydrogen generation storage, and this is of special interest in Scotland with its small regional flights. At the moment, Jet A1 needs to be moved out to the sites to make sure there's fuel available at these remote locations, but we could potentially have actual generation at location and then use. We're going to have potentially, because of the hydrogen hub concept, we might have multiple potential regulatory environments, multiple control systems, and also lots of parallel energy vectors being used at the same time. Refueling at site may involve many parallel fuel streams at a single location. So the energy vectors we mentioned previously, but also different grades of energy vector. So, for example, the hydrogen quality needed for fuel cells is very different from direct combustion, and you wouldn't want to mix the two. Also, airfields are highly controlled locations with multiple potential safety implicated interactions. Airspace design, so approach paths, go-around routes, and potential vent plume areas from hydrogen storage. EMC, EMI considerations for electrical systems. So, for example, there's just been talk about the installation of a large solar PV array at Edinburgh Airport. So if you have generation at site, you have sensitive navigation and communications equipment to airfields. Potential physical interactions, so solar PV reflecting light, turbines affecting radar, or obstructions that can be collided with. And also you have concerns around security and maintenance access, including remote access. A lot of hydrogen systems are remotely monitored or controlled, and there's also cybersecurity concerns and concerns around people getting access to the equipment and sensitive and safety related equipment at the site. Next slide, please, Jane. So pipelines and hydrants. Normally with hydrogen, you want to have a nice free open space, but obviously if you're running in trenches and pits, you have these constrained environments where you're venting into. Liquid hydrogen introduce the cryogenic hazards, can condense water vapor and oxygen out of the atmosphere, and I'll raise a specific concern here around if you get LOX, so liquid oxygen, from tarmac, it's explosive. Not something a lot of people are aware of, and you need to be aware of that. Development is likely to be incremental and iterative, so we need to make sure our management structure is in place to actually manage change. Lessons are learned and shared quickly, and we potentially have multiple different and diverse stakeholders. But a real advantage of the aviation sector is you do have this overarching regulatory framework through ICAO. This has been a challenge in the hydrogen sector. There's been multiple different approaches depending on the environment, but actually the aviation sector may have an advantage here. You need to talk to different regulators who are already talking about in these linked sectors, but also learn from other sectors that are further ahead than the aviation sector. So road and marine principally. Next slide, please, Jane. So all of this is leading towards why I mentioned Buncefield at the start. So there's lots of reasons and underlying causes of the Buncefield incident, but one of the underlying challenges was that at Buncefield they had multiple different systems and monitoring systems running in parallel. This will be a challenge going forward with the aviation sector, and it's a consistent challenge with the whole energy transition. Sectors are not going to be isolated from each other. Aviation, rail, marine, road, chemical process industry are all going to be interacting and dealing with each other, and hydrogen is an energy vector that cuts across multiple different sectors. So we are going to need to learn and iterate together. Pass back to you, Nigel.
You're just on mute, Nigel.
Yes, that's another pound in the pot there. Ed, thank you very much, and that clearly gives an overview of some of the issues around managing safe use of hydrogen going forward, and specifically around cryogenic use of hydrogen. So, some areas that need to be looked at very carefully. But it does give some advantages in terms of gravimetric density. There's actually a question on that I'll come back to. But while we're taking the questions, if I could just ask anyone in the audience, to all of you in the audience, to reflect on what are the next steps that you would like to see happening in order to help us move forward this work on zero emission aviation. Is there a need for events like this? Are there other activities that you think should be taking place? It'll help myself and Patrick just to take away some of the thoughts from today's event and then work out what we might do next. But back to the questions, and delighted to see there's some questions coming up in the chat. I think the one I'd like to start with, hopefully a fairly quick one, is for Ruan, and it's about the way you actually test and certify the hydrogen storage cylinders. So it's a question from Nick Hart of ITM Power about what's the kind of approval approach that you would have to go through for your cylinders, and which particular regulations. And I think in this particular one, it's worth also reflecting on. There was a comment by Stephen Cunniff of Doosan Babcock about the TPED regulations. And there's been a few lessons learned there about making sure that depending on how you're using hydrogen cylinders, that you consider the TPED requirements as well as the other requirements. So Ruan, any comments on that one?
Yes, no, thanks Nick Hart for that question. And if you have any more in-depth questions, please don't hesitate to get in contact. But for the regulatory aspect of hydrogen tanks, we are currently looking at British Standards EN 12245 specification and standard, as well as ISO 41119-1 to 5. So those are the two on top of obviously TPED standards. TPED is usually focused towards the transportation of hydrogen tanks within drones and smaller applications. And for the actual certification of the tank itself for larger applications, we're looking at the ISO and British Standards specifications.
Thanks, Ruan.
No problem.
And Stephen, this brings in the question around drones and the storage of hydrogen, which is the subject for another question. How do you see the market playing out in terms of use of compressed hydrogen or liquid hydrogen for drones? Does that start to segment in terms of the size of drone, the kind of distance you're planning to carry them? And there's probably another question that Ed might pick up on is how you actually refuel a liquid hydrogen drone. But let's start with the drone itself, Stephen.
Yeah, it's a good question. I think initially the focus should be on gaseous hydrogen. There's still major advantages that can be had with regards to increasing range. The advantages of the shift system is something we're interested in seeing how that would play out in a drone. Additionally, standardization is important, and I think we need to get improved standardization of the Type 4 bottles themselves as the drone market develops. Realistically, the way we see it is once beyond visual line of sight potentially takes off, once that regulation takes place, the commercial drone market will increase massively. And I think that's where standardization of the kind of gaseous hydrogen and the refueling of that initially is where the focus should be. However, looking at moving to larger payloads and cargo drones potentially, then you could look at the liquid hydrogen piece in that. But there's definitely, I think, enough to work with gaseous hydrogen in kind of light unmanned delivery drones and inspection services.
Thanks, Stephen. And Ed, do you have any sort of observations around the deployment of those two types, gaseous and liquid hydrogen, from the refueling perspective? Is there, for example, will liquid hydrogen not be restricted to, but mainly carried out in larger airports which have the infrastructure and the capability?
I mean, I think it would be a volume question, really. If you're doing relatively small amounts, I mean, even at airports now, most refueling is still quite a manual task, and it's you need to have a throughput of liquid hydrogen because it does gas off. It is constantly boiling off, and so you need to make sure you're generating, compressing, and using it as quickly as possible. Otherwise, it's not efficient. So I suspect it'll probably be driven by economies rather than anything else. And I know there was, I mean, I'm kind of something I've thought about from talking to Stephen is also the degree of automation we can see. If we start to move to sort of large volumes of cargo drones, do we want to start automating that packing and management side of it? And I think there's that broader question of automation generally in this, not just in the aviation, but across sectors. I think that's going to be an interesting challenge as well. It's kind of not ancillary to your point, but I think that there's a real question there. You know, we're moving towards like an Ocado type system of automated packing and drone sort of storage and potentially refueling as well. But yeah, I think on compressed, I mean, it's always a challenge with hydrogen. You lose it. Liquid hydrogen, it's even more concerning. You need to make sure you have the throughput to make sure you're not using it. But from a safety perspective, I mean, cryogenic hydrogen introduces a whole lot of interesting challenges for aviation structures because we are more reliant on the skin takes some of the loads in comparison with more sort of agricultural, better phrase, structures that are more robust. So if you have a release, you don't have those cryogenic concerns aren't as serious. You know, if you've got an aircraft and you have a cryogenic release inside it, the skin is suddenly becoming brittle. There's a lot of challenges there for liquid hydrogen in the aviation sector, I think.
So again, I think fair to say, Ed, that's the whole system approach. You know, think about all of the factors, how they interact, the potential consequences. So we need to be on top of these to make sure it's delivered safely. So yeah, Cedric, I'd like to come back to the question around the actual powertrain design. And yeah, we've got a couple of questions. I think the first one, which is a nice one, is from James Ferguson, who's at EMEC in Orkney, and it picks up on how you might use supercaps as part of the powertrain. But this comes back, I think, to a fundamental question: is when you design the powertrain system, how you look at the energy of the overall package and the power delivery of the package. And Cedric, where do you see things going with the fuel cell systems? Will it be hybridized with batteries? Will supercaps have a part to play? Lightweighting, how might that evolve in terms of the approaches and the materials and the designs?
Thank you, Nigel, for the question. Indeed, so it's always, as I mentioned, in the process, we always have to balance the fuel cell size versus the battery size, and we try to minimize it as small as possible for especially the aircraft application because of the battery specific gravimetric weight, and that is potentially a good competing solution, the supercapacitance. Coming from my experience, we have used supercaps on the commercial vehicle trucks or buses with fuel cells. So in the past, it's even public domain. I think that Wrightbus did that as well for terrestrial and mobile applications. For aircraft, it's totally open. So that means that there's no precedent per se. So you can use supercaps plus battery, lithium-ion batteries, or only supercap to help. What is important, and if I remember well the question, it was around the possibility to size the propulsion system for takeoff and for cruise, and how to balance those two with the rest of the powertrain system. So that's what everyone is going through at the moment to reduce the weight of the overall system. If we can have only supercap for just burst for some seconds, because supercaps is only operating for some seconds, then we should use them, and that will help to reduce the size of the buffer, what I mentioned in my presentation, the buffer system, which I said just battery, but it could be supercap. That will help. The battery, as we all understood, is not the solution to go ahead at the moment as the main propulsion system or the main source of energy for the propulsion system, because it's too heavy even in the next 10 to 15 years.
Yeah. Cedric, that's great. Thank you very much. Ed, did you have anything you wanted to?
I was just going to mention it. I really liked Cedric's approach of defining the system boundary, and it's one of the things I'm a safety engineer, so always consider the off-nominal scenarios as well. So, go around obviously has pretty intense or kind of evasive manoeuvres, drives some quite intense thing. That's just a general thing, but I'm sure Cedric's already covering that. But it's just one of those things of making sure you clearly define all the states your system might be in, including the ones you don't really want it to be into, but you need to account for. Just encourage people to take a good systems engineering approach as Ricardo laid out.
Excellent. Thanks, Ed. So I'd like to take this opportunity to thank all of the speakers for taking part. It's been a really informative session. It covered quite a lot of ground. It's pretty much a taster, but I think there's a lot more to start to look at in more detail. And hopefully we'll actually pick this up in some future events. Hopefully Patrick will be doing some of this work with SEED going forward. Just my reflections on the session today is there is clearly strong interest in actually developing zero emission aviation. Linked to that, it's not just about replacing the planes that we currently have. It's also thinking about new ways of moving goods around in particular. So drone deliveries, and hopefully Stephen will start to see some more deployment of the drones with hydrogen systems coming through in the next year or so. Could play a really important part in starting to move logistics off the roads, and in particular in areas where you've got more difficult access. Islands and the Highlands of Scotland could be perfect places to test this out on a wider level. And so hopefully you've enjoyed the session this morning. You found it informative. If there's any further questions that you'd like to follow up on, my contact details, I can circulate that around together with the information from Patrick. And I'd just like to take this opportunity now to thank SEED for this joint event, and just hand over to Patrick for a few comments to wrap up today.
Well, thank you, Nigel. It's always a pleasure working with you. I always rely on you to pull together an excellent package and presentation. I can see that everybody in the chat box has been saying very much the same. So thank you to everybody for your contributions. There are a couple of other questions which in the chat box, which we'll try to address offline. So what I'll also try to do is look at some of the contributions that various companies have made in terms of the offers presented, and put something up either on the SEED website, or talk to Nigel about how best that we can broaden the community inputting into this area, and let people know what other people are doing. Thank you for those saying we should have to do more events like this. There were questions in the chat box about what they might look like. Love to hear from you about especially the SEED community. We want the SEED community to get involved. There have to be opportunities to make things, to contribute things, as we're seeing in the chat box, and that's what SEED is here for, to create that community that can contribute to the development of these interesting and absolutely significant ideas as we move towards net zero. So thanks once again from SEED. Please do get in touch if you want to know more about us. You already know a lot about Nigel, otherwise you wouldn't have been here on this presentation. And thanks to the speakers too. Thanks to Jane in the background, and Josie, who have been pushing buttons and making slides work, and turning off videos and various things like that. And without those guys, it'd be almost impossible to run these events. All right, bye-bye from me.
Thank you. Goodbye.